Hello everyone, welcome to our presentation. Our project topic is grammar error correction. Let's begin with introduction. For non-native speakers, it's pretty common to make grammar mistakes in their daily life. Poor grammar may lead to some problems such as misunderstanding in face-to-face communication and poor academic reports or paper quality. So our goal is to build a model that takes a potentially erroneous sentence as input and outputs the correct version of this sentence, which help non-native speakers in English learning. Then let's talk about source of data and processing. Our data comes from two sources. One is from a teammate's talk writing with perturbation extracted from FCE dataset. We can extract the real error pattern from M2 format annotation and reverse it as our perturbation scheme, which is in the form of word correct, word wrong. Take annotated 1 as an example. The word are has a subject-verb agreement error, and its correct form is the word is. So we can build perturbation scheme is are. Similarly, we have good gold. We can store all this perturbation in a Python dictionary. Then we can generate new data samples from previous perturbation schemes. Suppose we have a correct sentence. In the eyes of adults, he's a good boy. We can create wrong sentences by replacing is with are, good with God. So in this way, we create 2 new data samples, and more data samples are shown in the table below. Even though the previous data generation method covered most of the error types, some grammar error types can be only created by adding or deleting something from the correct sentences. So we need C4-200M dataset, which contains some other grammar error types, such as missing words and punctuation misuse. Like the second example here, there is a missing determiner error in the input sentences. As you can see that the C4-200M dataset also contains some special characters which are not English. So we also remove all these characters for data cleaning process. Finally, we combine these 2 datasets to obtain our final dataset. The best model we have is a fine-tuned T5-based model, which contains 220 million parameters. This model comprises an encoder, a decoder, and an LM head. The encoder contains 12 transformer blocks, each with self-attention and feed-forward MLP. The decoder also contains 12 transformer blocks. Besides the previous 2 layers, it also contains cross-attention. To train a T5 SIG-to-SIG model, both input and output sentences in the dataset need to be tokenized. The model requires the tokenized output as labels. We also use weights and biases to track the process of training. It can automatically save the loss and score during training and plot training curves.
For the baseline model, we use the pre-trained GPT-2 medium model. It contains 355 million parameters. It comprises 24 decoder blocks and an LM head. Each decoder contains 2 layers, mask self-attention layer and the feed-forward MLP layer. To create acceptable training data for the GPT-2, we combine our wrong sentence enclosed in S and /S and our correct sentence enclosed in P and /P with 4 greater than sign in between. For quantitative results, we have 2 kinds of measurements, ROGUE-1 score and acceptance rate. ROGUE-1 score reflects the similarity between the output and the label. We calculate the precision and recall based on the generation and the references, and the ROGUE-1 score is the standard F1 score of the precision and recall. We use the GPT-3 OpenAI playground and design a prompt for GPT-3 to decide whether our model generation is grammatically correct or not, and calculate the proportion of the sentence successfully correct by the model. We can see that the T5 model trained on combined data is our best model. It has the highest acceptance rate and the second highest ROGUE-1 score. There is something interesting we find about the GPT-2 model. We can see that our GPT-2 model has a relatively high acceptance rate, which is almost like the T5-based model, but its ROGUE-1 score is relatively low. It's closer to the T5 model. This means that although the result GPT-2 generate is grammatically correct, they are a little bit off from what we want originally. For the qualitative result, we can see that the GPT-2 model sometimes will generate unrelated word, which leads to low ROGUE-1 score we discussed previously. And our T5-based model works pretty well on these examples, and it can detect multiple errors in one sentence. There are 2 kinds of errors we find our model can detect. The first is the subjunctive mode. We can see that our model corrects the sentence based on word should, but fail to consider the whole context. The second one is like this example. The dad found the boy and he was happy. This sentence is grammatically correct, and even Grammarly can detect any mistake, but it's misleading. We don't know who was happy, the dad or the boy. We think our model worked pretty well. We fed our model with large amount of data, and the quantitative and qualitative results are pretty good. As for learnings, one thing we learn is to create some new data by ourselves instead of taking them all from the internet. Secondly, we measure our model performance in our own way. We combine the ROG1 score with the acceptance rate we created. Also, it's always good to make a plan. With the plan we made in our proposal document, we can finish this project friendly and with high quality. These are all the content for our presentation today. Thank you.